On August 25, 2012, a spacecraft called Voyager 1 crossed a boundary no machine had ever crossed. And every headline on Earth said the same thing. Humanity has left the solar system. Those headlines were wrong. Voyager 1 is moving at 61,000 kilometers per hour. That is almost 20 times faster than a rifle bullet. It has been flying, without a single stop, for almost 50 years. And if you measure the solar system the way gravity measures it, out to the far edge of the Oort cloud, where the sun finally lets go, then Voyager has covered a fraction of 1% of the way out. It needs roughly 30,000 more years to finish the trip. Every human civilization that has ever existed, every empire, every religion, every language, fits inside 1/5 of that weight. So here is what we are going to do tonight. We are going to design the ship that actually leaves. And by leaves, I do not mean throwing another dead machine past a boundary. I mean living people, going and staying gone. The budget is unlimited. The physics has to be real. And I will tell you what is proven and what is hope every single time. And I will make you one promise before we start. This ship is going to fail. It will fail more than once, in places you do not expect. And the failure that finally kills, it has nothing to do with engines. It starts with a machine that is dying right now, 25 billion kilometers from here, and the small group of people trying to keep it alive. In November of 2023, in a building at the Jet Propulsion Laboratory in Pasadena, California, a team of engineers watched the oldest active spacecraft in history lose its mind. Voyager 1 did not go silent. Silence they had plans for. Instead, the spacecraft kept transmitting, right on schedule, at full strength. And what came down was garbage, a repeating pattern of ones and zeros with no meaning in it at all. The radio worked. The antenna held its lock on Earth across 25 billion kilometers. But the machine behind the radio had stopped making sense. The way a stroke patient can keep speaking in a clear voice while the words come out scrambled. Understand what this team was up against, because the numbers here are almost comedy. Voyager 1 launched in September of 1977. Jimmy Carter was president. Star Wars was playing in theaters. The onboard computers hold 69 kilobytes of memory, which is less than a single photograph on your phone, and they run about as fast as a digital wristwatch from that same decade. This is the machine that carried humanity's first close portraits of Jupiter and Saturn, and it did all of it with less computing power than a modern hotel keycard. And it is far. The radio signal, moving at the speed of light, the fastest anything can move, takes about 22.5 hours to reach Earth. Send a command back, and you wait another 22.5 hours to learn what happened. Every question is a 45-hour round trip. There is no live troubleshooting. You talk to Voyager the way you talk to the past, one letter at a time, and you wait 2 days for the reply. Now look at the people in that room. Most of the engineers working the problem were not alive when this spacecraft launched. The project manager, Suzanne Dodd, joined the mission in 1984, and she is one of the last links to its early years. The men and women who actually designed these computers, who knew every wire by heart, retired decades ago. Many of them have died, and the documentation they left behind was written for a world of paper. Schematics in boxes, memos typed on machines that no longer exist, describing custom hardware that was obsolete before most of the current team was born. So the rescue of Voyager 1 in 2023 looked like nothing else in modern engineering. It looked like archaeology. The team pulled decades-old documents out of storage. They tracked down retired engineers and asked them what they remembered. They rebuilt from paper and memory. A mental model of a computer nobody had manufactured since the 70s, because the only people who fully understood it were gone, and the machine itself was a 2-day round trip away. Speaking gibberish, it took them months, and the answer, when they finally cornered it, was one chip. A single memory chip in the flight data system had died. After 46 years of cosmic radiation and cold, one small piece of 1970s hardware finally quit, and it happened to hold a section of the code the spacecraft uses to package its messages. Everything Voyager tried to say was passing through that dead spot and coming out shredded. There is no fixing a chip at 25 billion kilometers. There is no spare, no repair visit, no reboot from the factory. What the team could do was rewrite the software around the wound. They carved the affected code into pieces, found unused corners scattered across that tiny 69-kilobyte memory, tucked each piece into a corner, and stitched them together with instructions so the computer could hop across its own dead tissue without noticing. They transmitted the surgery in April of 2024. Then they waited 45 hours. The longest 45 hours that building had seen in years. And the signal came back clean. Engineering data first. Science data, a few weeks later. A machine older than most of its own operators. Blinded by a wound nobody could touch. Talked back to Earth in full sentences because a team in Pasadena performed brain surgery by mail on a computer from the disco era. Hold on to that story. Every piece of it matters later. The dead chip. The retired experts. The knowledge that had to be dug out of boxes. Because tonight is about a journey 1,000 times longer than Voyager's. And this rescue is the best-case scenario for how such a journey goes. But first, sit with the uncomfortable part. Voyager 1 is, by any honest measure, the most successful thing human beings have ever built. It is the fastest object we have ever thrown away from our star. It has outlived its designers, outlived the Cold War that funded it, outlived every computer of its generation. And it is still doing science, with 400-year-old physics and a nuclear battery that loses about 4 watts of output every year. Which means sometime in the coming years, perhaps in the 2030s, it may finally run out of breath and go quiet forever. That machine, our champion, our record holder, has been driving away from home at 61,000 kilometers per hour since before the Walkman was invented. And it is barely out the front door. The headlines in 2012 said it left the solar system. NASA itself was careful with the words, and almost nobody noticed the care. What Voyager crossed that August was real, and it was historic. And it was also something much stranger and much smaller than leaving. Which raises a question most people have never actually asked out loud. Where does the solar system end? Picture the solar system. Go ahead. Picture it. Whatever appeared in your head, I can probably describe it. The sun in the middle. 8 planets in neat rings around it. Maybe with Pluto sulking at the edge. That picture hangs in every classroom on Earth, and that picture has quietly lied to you your whole life, because it has an edge, a last orbit, a place where the map runs out and the solar system is over. The real thing does not end there. The real thing barely gets started there. Let me take you out, layer by layer. Neptune, the last planet, orbits about 4.5 billion kilometers from the Sun, 30 times farther out than Earth. For most people, that is the finish line, and for the first layer of the real solar system. It is the starting gun. Past Neptune, you enter the Kuiper Belt, a wide ring of frozen leftovers from the solar system's construction. Billions of icy bodies, Pluto among them, stretching out to roughly twice Neptune's distance. New Horizons, one of the fastest spacecraft ever launched, took 9 years just to reach the near side of it. Keep going, and you eventually hit the boundary Voyager made famous. And this one needs a proper introduction, because it is the boundary in every headline, and it is not what people think. The sun does not just shine, it blows. A constant hurricane of charged particles called the solar wind pours off its surface in every direction. 1,000,000 tons of it every second. And that wind inflates a bubble around our star the way breath inflates a balloon. Inside the bubble, the sun's weather rules. Outside it, the thin gas between the stars pushes back. The skin of that bubble, the place where our star's breath finally stalls against the galaxy, is called the heliopause, and it sits a little over 18 billion kilometers out. That is the line Voyager 1 crossed in August of 2012. It is a real border, a measurable one. The instruments watched the solar wind die away and the particles of interstellar space rise, and for the first time a human machine was swimming in the material between the stars. The champagne was earned, but the heliopause is a weather boundary. It marks the edge of the sun's wind, and the sun holds its family with something that reaches enormously farther than wind: gravity. And gravity's grip goes out and out. And this is where the classroom picture dies completely. Starting about 1,000 times the Earth-to-Sun distance. Astronomers are confident the sun is wrapped in a vast cloud of icy debris called the Oort cloud. Nobody has ever photographed it. The objects are too small and too dark. But we know it is there because it keeps throwing snowballs at us. Every so often, a comet falls into the inner solar system on an orbit thousands of years long, arriving from a random direction. And when a Dutch astronomer named Jan Oort ran the arithmetic on those orbits in 1950, they all pointed back to the same answer: a reservoir of trillions of comets, a shell of frozen debris surrounding everything we know, bound to the sun, part of the family. The inner edge of that cloud begins far beyond anything Voyager has touched. The outer edge, the place where the sun's gravity genuinely fades against the pull of neighboring stars, lies as much as 100,000 times the Earth-to-Sun distance away. NASA's own description puts that edge well over a light year out, as much as halfway to the nearest star. So let me rebuild the picture in your head at honest scale, and I will use a road trip to do it. Shrink the whole solar system until the sun sits in Los Angeles and the outer edge of the Oort cloud sits in New York. On this map, coast to coast is the real solar system, all of it inside the sun's gravity. All of it, our home address. Where is Earth? Earth is 40 meters from the sun. Not 40 kilometers. 40 meters. Half a city block from downtown Los Angeles. Every human being who ever lived on that half block. The moon, the farthest any person has traveled, is 10 centimeters past it. A single step. Neptune, the last planet, the edge of the classroom poster, is a 20-minute walk from the sun, barely over a kilometer. The entire planetary system, the thing we call the solar system in every textbook, fits inside one Los Angeles neighborhood on a map the size of America. And Voyager 1, our record holder, flying since 1977. The fastest escaping object our species has ever produced. On this map, Voyager has traveled about 5 kilometers. After 47 years, it has not left Los Angeles. It has not left the neighborhood where it was born. The heliopause, it crossed the border in all the headlines, sits inside city limits, and the drive to New York has not meaningfully begun. That is the size of the thing we are trying to leave. The distance between the classroom picture and the real one is a factor of 1,000. And every plan, every engine, every dream of leaving that you have ever heard was priced against the classroom picture. Now, one detail before this chapter ends, because it changes the mission entirely. Nobody builds a ship just to reach empty cloud. If humanity leaves, it leaves for somewhere, and the nearest somewhere, the Alpha Centauri system, sits about 4 light-years out on our map. That is a second road trip past New York, roughly twice as far again. The Oort cloud is not the destination. It is merely the driveway. A driveway that our fastest machine will spend 30,000 years backing out of. 30,000 years. I keep saying that number, and I know it is not landing yet, because numbers that size never do. So in the next few minutes I want to make it land, using the only measuring stick that ever works on time, this deep. Us, 30,000 years is not a number. It is a wall of zeros, and human brains bounce off it. So let me walk you into it slowly, using things that actually happened. Start small. Go back 1,000 years. It is the year 1026. There is no England as you know it. No United States. No printing press. No gunpowder in Europe. The most advanced navigation technology in the Western world is a Viking longship. 1,000 years. And nearly everything you would recognize about civilization has vanished behind you. Voyager needs 30 of those. Go back 5,000 years. And you are watching the first cities rise in Mesopotamia. Writing has just been invented. Wedge-shaped marks pressed into wet clay to count grain and goats. The Great Pyramid does not exist yet. 5,000 years is the entire recorded history of the human species. Every king, every war, every book, every name we remember. All of it. Voyager needs 6 of those, stacked end to end. Now go all the way. Go back 30,000 years. The full length of the trip. And find the humans at the other end. They are living in the Chauvet cave in southern France, painting lions and rhinos on the walls by torchlight. And those paintings are so old that the rhinos went extinct. The torches went out, and the cave entrance collapsed and sealed itself before the first farmer planted the first field anywhere on Earth. Between those painters and you sits the invention of agriculture, the wheel, metal, writing, cities, nation, science, and spaceflight. The distance from them to us is the distance from Voyager's launch pad to the edge of the driveway. That is the exit. Painted cave to jet propulsion laboratory. And you still have not reached the next star. And here is where the problem stops being about distance and becomes something worse. Because a journey of that length is not a voyage. It is a relay race across generations of custodians. And the fossil record on human custodianship is brutal. Ask history a simple question. What is the longest any human institution has ever continuously operated? The Roman Empire ran about 500 years in the West. The Catholic Church, maybe the most durable organization ever assembled, has held together for about 2,000. The oldest continuously operating company on Earth was a Japanese temple builder called Kongo Gumi, founded in the year 578. And it lasted 14 centuries before collapsing into a subsidiary in 2006. Call 2,000 years the human record for keeping one project alive with one purpose. Voyager's exit takes 15 times longer than the all-time record, and the record holder had the advantage of operating on a planet with air, food, and replacement humans included. There is a sharper way to see it, and it comes from the spacecraft itself. Voyager carries a golden record, sounds and images of Earth, greetings in 55 languages, a map showing where it came from, the people who made it. Carl Sagan's team in 1977 understood exactly what they were building, because they were not building a message for a spacecraft's crew. They were building a message for whoever finds the wreck. The golden record is the flight plan of an object whose builders knew that nothing human would be waiting at the other end of its journey. No mission control, no receiving station, no nation that remembers launching it. They packed it a tombstone, and they were right to, because run the thought experiment forward. Suppose we simply waited out the 30,000 years. Suppose Voyager needed a course correction in the year 32,000. Who sends the command? NASA is an agency of a government that is 250 years old. The radio dishes that talk to Voyager belong to a network built in the 1960s. The engineers who understand its computers are already retired or gone. And that is 47 years in, which is 1/6 of 1% of the trip. You saw what 47 years did in Chapter 1. One dead chip. And the fix required digging paper to schematics out of storage and interviewing the elderly. Multiply that problem by 600. And you have the honest shape of a 30,000-year mission. It is a message in a bottle, and the civilization that threw it will not exist to see it wash ashore. So the slow road is closed. It was never really open. Coasting out of the solar system at Voyager speed means handing the mission to 600 consecutive generations of strangers and hoping every single one of them cares, funds, remembers, and understands. No species does that. Ours certainly has not. Which leaves exactly one direction to push. And every one of you got there minutes ago. If the trip is too long, shorten it. If 61,000 kilometers per hour takes 30 millennia, then stop crawling. Go faster. Say it out loud, and it sounds like a plan. In the next chapter, we are going to find out what that word actually costs. And I will warn you now, the price tag is the strangest number in this entire story. Every problem so far has been a problem of patience. From here on, it becomes a problem of physics. So let us set the target properly, like engineers. Because tonight we are engineers. The mission is a human lifetime. That is the whole specification. A crew boards the ship, and inside one working life. Call it 50 years. They get somewhere worth going. Not their grandchildren. Them. The moment a trip outlives its travelers. You inherit the relay race from Chapter 3. And we just watched the relay race fail 600 times in a row. So, 50 years is the wall. And everything tonight gets measured against it. Now do the arithmetic with me. It is short. And it is the most important arithmetic in this video. To cross the full solar system, out to the far edge of the Oort cloud, in 50 years instead of 30,000, you need to move roughly 600 times faster than Voyager. 600 times 61,000 kilometers per hour lands you near 37 million kilometers per hour, which is about 10,000 kilometers every second. And that number has a more famous name. It is roughly 3% of the speed of light. Read that again. Because it is the moment tonight's mission changes species. Beating the driveway, just the driveway, in one lifetime requires a vehicle moving at a meaningful fraction of the fastest speed the universe allows. And if you want the real prize, the second road trip, Alpha Centauri and its planets in those same 50 years. you need 8 or 9% of light speed, and closer to 10 if you would like time left over to slow down at the far end. 10% of the speed of light. 30,000 kilometers per second. Earth to the moon in 13 seconds. No object made by human beings has ever moved at 1% of that speed. The gap between our best and this target is not a gap you close with a bigger budget. It is a gap of 500 times. And it is the reason every serious conversation about leaving the solar system eventually stops being about telescopes and destinations and becomes a conversation about one thing only: thrust. So let us start designing, and let us start the way every engineering project in history starts. With wild optimism and a clean sheet of paper. Here is our ship. Version 1. I am going to keep it almost insultingly simple, because simple is honest. 1 crew member, 1 small cabin with air, water, food, and a chair. Call the whole package 1 ton. About the weight of a small car. No cargo, no laboratory, no landing craft, no luxuries. A human in a can, pointed at the stars. Every spacecraft that ever flew was, at its heart, this object. And 1 ton is about the most generous simplification physics will let me get away with. Our job is to throw this can out of the solar system at 1/10 of the speed of light. And I will be straight with you. Standing here at the drawing board, the job looks doable. Rockets exist. Rockets get faster every decade. We went from the Wright brothers to the moon in 66 years. From room-sized computers to phones in 50. The story of technology, as everyone tells it, is a story of walls turning into speed bumps. Give the engineers a century, people say, and they will hand you the stars, because they always have before. Here is why this time is different. And I want you to hear it before we open the toolbox, because it is the honest heart of this whole night. Every machine you have ever ridden in obeys 1 rule, so old and so quiet that nobody thinks of it as a rule. It carries its own push. The car carries the gasoline. The jet carries the kerosene. The rocket carries the propellant. And the moment a vehicle carries its own push, it is trapped inside a piece of mathematics written down in 1903 by a deaf Russian schoolteacher. A single short equation that has quietly strangled every interstellar dream of the last 100 years. The equation does not care about budgets. It does not care about deadlines, or national pride, or how badly a species wants to see another sun. It takes exactly 2 numbers. How fast your exhaust leaves the nozzle and how fast you want to go. And it hands back the price in fuel. Feed it a highway trip and it asks for a gas tank. Feed it the moon and it asks for a skyscraper. In the next chapter, we are going to feed it 10% of the speed of light. And it is going to hand back a number that does not fit inside the universe. The equation is called the rocket equation. Konstantin Tsiolkovsky wrote it down in 1903. And I am going to skip the biography, because the man matters less than the trap he found. What he discovered fits in 1 sentence. A rocket is a machine that has to lift its own lunch. Here is the whole mechanism, and once you see it, you cannot unsee it. A rocket moves by throwing propellant out the back. More speed means more propellant. But propellant has weight. So now the rocket is heavier. So it needs extra propellant just to push the propellant it is already carrying. And that extra propellant has weight too, and needs its own extra. And that extra needs extra. The cost does not add up. It multiplies. The way debt multiplies when you pay off one credit card with another credit card. and the interest rate is set by one number alone: how fast your engine can throw stuff out the back. That exhaust speed is everything. If your desired speed is lower than your exhaust speed, the equation is polite, and your fuel bill stays reasonable. Push past it, and the bill starts compounding. Every additional exhaust speed worth of velocity roughly triples the whole rocket, fuel and all, on top of every tripling that came before. This is an exponential, the same mathematics as a nuclear chain reaction, except pointed at your wallet. Now let us run our ship. In public. On the board. Our can weighs 1 ton. The best chemical rocket engines humanity has ever built. The hydrogen-burning engines that flew on the space shuttle throw exhaust at about 4.5 kilometers per second. Our target is 30,000 kilometers per second. Divide those, and the target sits 6,600 exhaust speeds away, which means the equation is going to compound our ship 6,600 times in a row. I want to be careful here, because the answer is not a big number. Big numbers are things like the national debt, or the number of grains of sand on Earth, or the number of stars in the sky. Those numbers are babies. The fuel mass this equation demands, measured in ton, is a number with nearly 3,000 digits. For comparison, count every atom in the observable universe. Every atom in every star of every galaxy, and you get a number with about 80 digits. Our fuel bill has 3,000, so take the universe, all of it, grind it into rocket fuel. Every planet, every star, every black hole, every atom of gas between the galaxies. Pack it into a fuel tank behind our 1-ton can. You are not close. You are not 1% of the way there. You would need that entire universe of fuel, multiplied by itself dozens of times over, before the chemical rocket says thank you and delivers one human being to 10% of light speed. This is why nobody has done it. This is why nobody will ever do it with chemistry. The universe does not contain the gas money, and there is no version of trying harder that fixes an exponential. You cannot engineer your way past a number with 3,000 digits. You can only change the number, and the equation gives you exactly one lever to pull. Exhaust speed. Throw things out the back faster, and the trap loosens. Chemistry tops out around 4.5 kilometers per second, because chemistry is just electrons rearranging themselves between atoms. And electrons are weak, but atoms have a basement. And in the basement is the nucleus. And the energy locked in the nucleus is about 1,000,000 times greater than anything the electrons can offer. Which brings me to the first crew of human beings who actually tried to open that basement and drive to space on it. This part of the story is real. It is documented, and it remains one of the strangest chapters in the history of American engineering. In 1958, in a building in San Diego, a team of physicists began designing a spacecraft called Orion, and the propulsion concept was this. You build a ship the size of an office building. You give it an armored steel plate on the bottom, mounted on giant shock absorbers, and then you fly it by throwing atomic bombs out the back, one at a time, and detonating them behind the plate. A bomb goes off. The blast slams the plate. The shock absorbers smooth the kick into a shove, and the ship lurches forward. Then you drop the next bomb, then the next. A full interplanetary voyage would burn through hundreds of them. A Pacific War's worth of nuclear weapons. Spent as fewer, and the numbers actually work. The nuclear tests of that era proved that objects placed near a fireball, coated correctly, could survive with barely a scratch. and the physicists ran the engineering seriously for years. This was a funded government program with a staff and a test site. They flew a small conventional prototype on ordinary explosives in 1959, a little model called Hot Rod. And it worked. It rose and stabilized, and was recovered, and it sits in a museum today. The chief designers were Ted Taylor, one of the most gifted bomb designers alive, and a physicist named Freeman Dyson, who took a year away from Princeton because he believed this ship was worth his life's work. Their internal studies sketched voyages that still read like fever dreams. Saturn by 1970, and years after the program itself, in 1968, Dyson published the physics for where the idea could ultimately go. Enormous city-sized arcs, riding chains of hydrogen bombs toward a few percent of the speed of light. Crude, violent, and thermodynamically honest. To this day, the Orion family remains the only interstellar propulsion concept ever proposed that could have been started with a technology of its own decade. It never flew, and what killed it is the part worth remembering. The physics held up, the fallout did not. Launching Orion from the ground meant detonating hundreds of nuclear weapons in the atmosphere. And every launch would seed the air with radioactivity. And by the early 60s, the world had seen enough of that. In 1963, the United States, Britain, and the Soviet Union signed the Limited Test Ban Treaty, outlawing nuclear detonations in the atmosphere and in space. And Orion, a spaceship made of treaty violations, lost its future at the signing table, and the funding and the political will drained away behind it. Dyson wrote about the cancellation later, and the tone was heartbreak. This was the first time, he said, that a great door had been closed on humanity not by nature but by our own signatures. And he understood why the signatures were right. And he grieved anyway. Keep Orion in your pocket as we go, because it teaches the lesson this whole night runs on. The first wall between us and the stars was never purely physics. The bomb ship cleared the equation and crashed into the species that built it. Walls come in layers. But set the treaty aside, because the physics lesson still stands. The nucleus works. Nuclear energy shattered the chemical ceiling, and Orion proved on paper that exhaust speeds of dozens, even hundreds of kilometers per second, were purchasable. The equation that laughed at chemistry stops laughing when you bring nuclear fire. So the obvious question is what happens when you stop throwing bombs and start building an actual nuclear engine? Something controlled, contained, continuous. Something you could, in principle, ride without a treaty and without an atmosphere to poison. 15 years after Orion died, a small group of engineers in London decided to find out, and they did it in the most British way imaginable. After work, in a pub, for 5 years, between 1973 and 1978. On evenings and weekends, roughly a dozen members of the British Interplanetary Society met in the back rooms of London pubs and did something no government on Earth was doing. They designed a complete starship, end to end. And they did it to answer one question that hung over the whole field like a dare. Is interstellar flight possible with physics we already understand? Or is it fantasy? Nobody knew, because nobody had ever done the full engineering. Every tank, every pump, every gram accounted for. Talk was cheap, and papers were partial. This group decided somebody had to run the entire problem. And since no agency would pay for it, they did it for free, with slide rules and early calculators, pint glasses on the table. After their day jobs, they called the project Daedalus. and the machine they produced still casts a shadow over every Starship study since. Daedalus was a robot probe aimed at Barnard's star, about 6 light-years away, with a mission clock of 50 years. One working lifetime. The same wall we set in Chapter 4. To hit that clock, it needed to cruise at about 12% of the speed of light, and the engine they designed to get it there was fusion, the fire of the sun itself, but run in a way no power plant on Earth attempts. The mechanism sounds like science fiction and is bolted to real physics at every joint. You manufacture hundreds of billions of tiny fuel pellets, each one a frozen pea of deuterium and helium-3. You inject them into a reaction chamber at a rate of 250 pellets every second, and as each pellet arrives, an array of electron beams hits it from all sides at once, crushing it so hard and so fast that its atoms fuse. Each pellet becomes a miniature star that exists for a fraction of a second. A controlled micro-detonation, and a magnetic field cups the explosion like a catcher's mitt and throws the plasma out the back at 10,000 kilometers per second. 10,000. Chemistry gave us 4.5. This is 2,000 times better. And at exhaust speeds like that, the rocket equation finally comes to the table and negotiates. The compounding curse that demanded a universe of fuel now demands something merely enormous. 250 explosions per second, sustained for years, and the arithmetic closes. But watch what the equation takes in exchange, because it never simply surrenders. The Daedalus probe's science payload, the actual point of the mission, the cameras and instruments that would reach Barnard's star, weighed about 450 tons. The vehicle that delivered it weighed 54,000 tons, and 50,000 of those tons were fuel. Fully fueled, Daedalus outweighed the largest aircraft carrier the United States Navy has ever floated, and 92% of it existed to be burned. And it was a one-way bullet with no brakes. A flyby. After 50 years of flight, Daedalus would cross the entire Barnard star system in a few days, cameras running the whole way, and then continue into the dark forever. The pub engineers did not include a deceleration system, and their reasons were not laziness. Stopping would have required hauling fuel to burn at the far end, and hauling that fuel would have ballooned the ship from 54,000 tons toward 500,000 or more. The equation charges you for every gram, and it charges compound interest. And the team drew the only honest line they could afford. Look closely as we pass. Wave. Then there is the detail I love most, the one that tells you these men were serious. The fuel itself, that helium-3 in every pellet is a fusion fuel with almost magical properties and one inconvenient flaw. Earth barely has any. The planet's entire accessible supply would not fill Daedalus's tanks 1,000th of the way. The pub team knew this, refused to cheat, and followed the logic where it led. The gas giants have helium-3, drifting in their atmospheres in vast quantities. So the Daedalus plan, stated plainly in the published study, called for a fleet of robotic factory balloons floating in the atmosphere of Jupiter, separating helium-3 for 20 years, with tanker craft ferrying it up out of Jupiter's gravity to an orbital shipyard where the probe would be assembled. Sit with what that means. A dozen engineers, working unpaid in the evenings, set out to prove starflight was possible with known physics, and they succeeded. And along the way they discovered the true entry fee. Before humanity sends one robot to one star, humanity first industrializes the outer solar system, mining infrastructure at Jupiter, orbital shipyards, a civilization operating comfortably across billions of kilometers. all of it as the prerequisite, the warm-up act, for a single unmanned flyby. The study was published in 1978, and here is its strange legacy. Nobody ever found the fatal flaw. Fusion research has moved on and refined the details. Ignition schemes have changed, and the core verdict has held for nearly 50 years. Daedalus remains the closest thing the field has to a proof, cited to this day, that the rocket equation can be beaten by known physics. At civilization scale, for a rabbit. So, on our whiteboard, the picture has genuinely improved, and I want to be fair about that. Because tonight is not a story about impossibility. Fusion is real. The sun runs on it. Laboratories on Earth have ignited it. And in 2022, a facility in California finally coaxed more energy out of a fusion reaction than the laser energy delivered to the target. The engine class that Daedalus imagined violates nothing. Give the species a century or two of engineering, and a machine in that family can exist. Our 1-ton Ken from Chapter 4 is dead. Though, look at what replaced it. To move even a robot at 12% of light speed, the vehicle grew to 54,000 tons and swallowed the output of a Jupiter mining industry. The moment we put humans back aboard, with their air and food and shielding and their stubborn insistence on slowing down at the destination, that number does not grow politely. It detonates. But before we even get to the humans, there is a bill we have skipped. And it is the biggest one on the table. 50,000 tons of fusion fuel is not just mass. It is energy. An amount of energy with a shape you have never been asked to imagine. And it is time, somebody asked. How much power does it actually take to throw something across the gap between stars? Next chapter, we open the electric bill, and I will show you why the answer embarrasses every power grid on this planet combined. There is a bill hiding inside every conversation about starflight, and almost nobody ever reads it out loud. People argue about engines. People argue about fuel tanks and exhaust velocities and mission clocks. And underneath all of it sits a number that does not care which engine you pick. Because it is not an engineering number at all. It is the raw price of speed itself. Here is the rule, and it is worth one slow sentence. The energy of motion grows with the square of velocity. So, every time you double your speed, you multiply your energy bill by 4, and by the time you are moving at starflight speeds, that curve has left every human reference point far behind. Let me make it physical. A rifle bullet moves at about 1 kilometer per second, and it carries enough energy to kill a person. Take an object, the weight of a paperclip, a single gram, and push it to 10% of the speed of light. And that paperclip now carries the energy of roughly 100 tons of TNT. 1 gram, a large truck bomb, folded into something you could lose in the carpet. That is what velocity does when you feed it. And we are proposing to feed it a ship. So let us open the Daedalus bill. Because the pub engineers were honest enough to run it. And their fuel tanks were 50,000 tons of fusion fuel for a reason. Ask what it takes to fill that tank. And the answer stops being an engineering number and becomes a civilizational one. Add up every power plant on Earth, every coal furnace, every reactor, every dam, every wind farm, every solar panel, every car engine and jet engine and cooking fire. The entire energy metabolism of 8 billion people. Run all of it, everything, at full output, and pour every joule into that one fuel tank. Filling it takes about 30 years. 30 years of human civilization's total energy production. As the entry fee for one robot probe. No crew, no cargo, no brakes. that waves as it passes the destination. Put a price tag on it if you want the shape in dollars, at the rates you pay on your own electric bill. That tank holds hundreds of trillions of dollars worth of energy, several times the yearly economic output of the entire planet. And that buys the fuel once, for one vehicle, with nothing left over for the Jupiter mining fleet that gathers it, the orbital shipyard that assembles it, or the decades of industry that make any of it possible. Now, I promised you honesty in both directions tonight. So here is the other side. This is not impossible. Nothing about it breaks physics. Civilizations grow, and their energy budgets grow with them. Humanity uses roughly 10 times the energy it used a century ago. And if that curve continues, there could plausibly come a century when 30 years of today's output is a rounding error in some future grid. The energy cliff is not a wall in the laws of nature. It is something more uncomfortable. It is a mirror. Because energy at this scale is never just sitting in a warehouse waiting for a good idea. Energy is the working blood of a civilization. It is harvests and hospitals and heat in the winter. And any species deciding to spend a planet's output on a starship is deciding, in the same breath, what it will not spend that output on. The question stops being, can we build the engine? The question becomes, what kind of civilization taxes itself at this scale? For decades, for a payoff that arrives after every voter who approved it is dead. Orion died of a treaty. This wall is made of the same material. Physics permits it, and then quietly hands the problem to the humans. And look at what our whiteboard has become while we were reading bills. We started this night with a 1-ton can. Chemistry demanded a universe of fuel, and we fired chemistry. Fusion works. Fusion is real. And fusion handed us a 54,000-ton vehicle, a mining industry at Jupiter, and a 30-year mortgage on the entire planet's power grid. All of it to deliver a robot that cannot stop. Every road we have walked tonight has failed in the same direction. The ship keeps growing. The bill keeps growing. Mass demands energy. Energy demands fuel. Fuel is mass. And around the wheel turns, grinding every design into something a civilization can barely lift. Which is exactly why the most interesting idea in modern starflight went the other way. In the spring of 2016, on top of a skyscraper in New York City, a group of very serious people announced a plan to reach another star within a single generation, with real money behind it, and one of the most famous scientists on Earth sitting at the table. And their breakthrough was a kind of judo move on everything we have built tonight. They looked at the wheel. Mass demands energy demands, fuel demands mass. And instead of pushing harder, they stepped off. They asked the one question our whiteboard has never asked. What if the ship does not carry the engine at all? April 12th, 2016. The top floor of One World Observatory in Manhattan, over 100 stories above the street. A Russian-born billionaire named Yuri Milner steps up to announce that he is putting $100 million of his own money into an attempt to reach Alpha Centauri. And sitting beside him, lending the project his name and the weight of his judgment, is Stephen Hawking. The program is called Breakthrough Starshot, and it is the most credible interstellar effort ever funded, with real physicists, real laboratories, and real published papers behind it. Their target speed is 20% of the speed of light. Hold that number against everything we have suffered through tonight. 60,000 kilometers per second, 1,000 times faster than Voyager. Fast enough to cross from here to the moon in about 6 seconds. Fast enough to reach Alpha Centauri in roughly 20 years. Launch to arrival inside a single career. The pub engineers needed 54,000 tons and a Jupiter mining fleet to hit 12%. And here is a press conference cheerfully promising 20. For a moment, standing at our whiteboard. This sounds like the ending of the movie. It sounds like somebody solved it. So let me show you the trick. Because there is a trick. And it is beautiful. And it is the whole point of this chapter. The rocket equation, the tyrant that has ruled every page of tonight, has exactly one weakness. It only applies to vehicles that carry their own push. Every compounding, every fuel tank the size of a universe, every ton of propellant hauling more propellant. All of it flows from that single assumption. So Starshot broke the assumption. The engine stays on Earth. The engine is light itself. Light carries momentum. And this is measured physics. More than a century old. Sunlight presses on your skin right now. Far too gently to feel. And a laser is simply light with discipline. Build a phased array of lasers on the ground. Acres of emitters across a high desert plateau, firing as one coordinated beam of 100 gigawatts, which is roughly the output of 100 nuclear power stations combined. Aim that beam at a mirror in space. And the mirror accelerates. No propellant on board. No fuel tank. Nothing for the equation to compound. Because the mass of the propellant aboard is zero. Tsiolkovsky's trap, undefeated for a century, simply has nothing to grab. The beam fires for about 10 minutes. That is the entire burn. 10 minutes of the most concentrated artificial light in history. And when it shuts off, the spacecraft is coasting at 20% of light speed. A dead arrow that will cross the Gulf to Alpha Centauri in 20 years, with its engine still sitting in the desert behind it. Now come look at the spacecraft. Because this is the reveal. And I have been setting it up all night. The vehicle is called a Starship. It is a single wafer of electronics about the size of a postage stamp, carrying cameras, processors, a transmitter, and a power source, attached to a light sail a few meters across and thinner than a soap bubble. The whole spacecraft, sail and all, weighs a few grams, less than 3 paper clips, lighter than the key to your front door. That is the payload that 20% of light speed actually buys. Not a ship, not a cabin, not a crew, not a robot the size of Voyager, not anything you could put your hand on without crushing it. Humanity's fastest and most credible plan for touching another star is a camera you could mail with a single stamp. And even that miracle requires a laser array drinking 100 power stations. And you already know why it has to be this small. During those 10 minutes under the beam, the sail pulls tens of thousands of gravities of acceleration. A chip shrugs that off. A human being turns to liquid at a fraction of it. Put people aboard and the acceleration must drop to something bones survive, which stretches the 10-minute burn into months. Which means the beam must hold its aim on a fleeing coin-sized target across millions of kilometers, continuously, for the better part of a year, while its power bill climbs from 100 power stations toward the full output of the planet and beyond. Slow the burn to save the crew. And the energy cliff from last chapter comes back with reinforcements. The judo move works precisely because there is nobody aboard. The Starshot physicists know all of this. It is in their published work. In the problem lists they maintain. Sail materials that must reflect almost perfectly or vaporize. Beam stability through a shivering atmosphere. A transmitter the weight of a coin whispering across 4 light years. None of it breaks physics. All of it is brutally hard. And every serious version of it shares the same silhouette. Grams go to the stars. People do not. And that sentence deserves to be said plainly, because it is the honest headline of our entire era, and it lands harder than any number tonight. We will learn how to send a camera to another star long before we learn how to send the person who built it. There is a real chance the first photographs of an alien sunrise arrive within the lifetime of someone watching this video, beamed home from a chip the weight of a coin, and that the species celebrating those photographs will be no closer to following it than you are right now. Sitting in that chair, our whiteboard has finally split in two. On the left side, the things that can go: wafers, grams, dead arrows that never slow down. On the right side, us, with our 70-kilogram bodies, and our air and our water, and our stubborn refusal to survive 10,000 gravities. But suppose we refuse the split. Suppose we insist, out of pride or loneliness or whatever it is that makes our species point at horizons, that people are going anyway, at speeds like these, aboard something big enough to keep them alive. Then we run into a problem no press conference has ever mentioned. And it is my favorite wall of the night, because it sounds like nothing at all. At these speeds, empty space stops being empty. Ask anyone what sits between the stars, and they will give you the same answer. Nothing. Space is a vacuum, the cleanest emptiness there is. And on paper, that answer is nearly perfect. The gas between the stars is so thin that a volume the size of a sugar cube holds one atom, maybe two. The vacuum chambers in our best laboratories on Earth are crowded rooms by comparison. Park a spaceship out there, motionless, and it could drift for 1,000,000 years without a scratch. The paint would outlast the pyramids. Now start moving, and watch the nothing wake up. The physics turning against you here is the same rule from the energy chapter, the one that never left. Energy grows with a square of velocity. It applied to our ship when we tried to accelerate it. And it applies with exactly equal enthusiasm to everything our ship runs into. At walking speed, a grain of sand is a grain of sand. At rifle speed, it stings. And at 20% of the speed of light, the arithmetic goes somewhere your instincts have never visited. Take a single hydrogen atom, 1 proton, the lightest and most harmless object in nature. At starshot cruising speed, your ship meets that proton with the energy of a particle fired from an atom smasher. An atom, one collision, and it does not tap the hull. It buries itself in, shattering chemical bonds as it goes, knocking atoms of your ship loose like a cue ball breaking a rack. One proton is nothing, so count them. Your ship is crossing 60,000 kilometers of space every second, and every sugar cube of that space holds its atom. Multiply the cubes across the face of a hull hundreds of meters wide, and the front of your vehicle absorbs something on the order of 1 billion atomic impacts per second. Every second. For 20 years, the gentle interstellar fog, the nothing, has become a continuous beam of radiation. And your ship is flying face first into it for the entire length of the voyage. A physicist would put it this way: at interstellar speeds, you are not traveling through a vacuum anymore. You are the target in a particle accelerator the size of the galaxy, and the beam never shuts off. That is the gas. The gas is the polite part. Now meet the dust, scattered through the space between stars, thin as ghosts. Our solid grain, soot and mineral flecks forged in dying stars, most of them far smaller than a red blood cell. They are magnificently rare. A small object might fly 1,000,000 kilometers between meetings. And at these speeds, every meeting matters. because the arithmetic on even the tiniest grain has gone insane. Run the numbers, and remember the paperclip from the energy chapter, because this is its evil twin, a dust grain weighing 1 microgram, 1/1,000,000th of a gram, invisible without a microscope. Meets your hull at 20% of light speed, carrying the energy of about half a kilogram of TNT, a grainid, delivered by something too small to see, arriving without warning at a closing speed that makes radar useless. And here is where the size of a crude ship betrays it. A wafer the size of a postage stamp presents almost no target, and might dodge the worst of the dust for 20 years. Our vehicle is a wall hundreds of meters across, sweeping through space like a net, and a net that wide, crossing that much distance, collects the drizzle. Across 2 decades, a hull that size takes these hits again and again. A slow drumbeat of detonations on the bow for the entire voyage. And the distribution has a tail. Dust comes in sizes. And while the big grains are rarer, they are out there. A 1 milligram grain. Still just a speck. The weight of a grain of sand arrives with the energy of half a ton of TNT. A 1-gram pebble. Something that would sit invisibly in the palm of your hand. Hits with the force of a small tactical nuclear weapon. The odds of meeting the pebble are genuinely low. The cost of meeting it is everything. And there is no armor in this story or any other that shrugs off a nuclear detonation on the bow. Against the tail of the distribution, you do not engineer. You pray. The Starshot team, to their credit, published on this problem honestly, and their spacecraft survives it in the most instructive way possible. The Starship is a wafer. It flies edge-on, presenting an edge thinner than a human hair to the storm. And its designers accept that the interstellar medium will drill and pit and erode it the whole way, sanding away layers of a machine that has no crew to protect and costs little to lose. Because the plan launches 1,000 of them and needs one to arrive. Attrition is the shield. Send a swarm. Sacrifice the many. Celebrate the survivor. You cannot fly a family that way. A human-rated ship cannot be a wafer flying edge-on. It is a habitat. Hundreds of meters of hull, wide enough to matter. And it cannot play the attrition game because every copy has people inside. The swarm strategy, the one honest answer anyone has found to the dust, is exactly the strategy that dies the moment the payload can die. So our ship needs what every ship in every ocean has needed since ships existed. It needs a bow that can take the sea. A wall at the front, thick and dumb and sacrificial, built to stand between the crew and 20 years of atomic sandblasting punctuated by grenade blasts, absorbing the beam and the detonations and the erosion so that everything behind it stays soft and alive. Simple enough. Armor the front. Engineers have armored things for 3,000 years. And this is just armor. Except, watch what happens to our whiteboard the moment we draw it. Because armor has a property that this particular ship cannot forgive. Armor is heavy. Let us design the wall. And let us do it the way engineers actually do it. Starting from what the wall must survive. The specification writes itself from last chapter. Stop a continuous rain of relativistic protons. Roughly 1 billion per second. For the full voyage. Absorb the routine detonations from microscopic dust, arriving at random across a bow hundreds of meters wide. Year after year. Survive the occasional half-ton blast from the milligram grains. Do all of it passively, with no repairs from outside, because there is no outside crew at 60,000 kilometers per second. And keep doing it for decades without once failing. because the first failure lets the beam through to the people. There is only one design that honestly answers that specification, and it is the oldest design in warfare. Mass. A thick slab of dense material riding ahead of the ship. Meters of layered carbon and ceramic and metal, containing nothing delicate. No wiring, no plumbing, no instruments. A wall whose entire career is to stand at the front and be slowly destroyed in place of everything behind it. Erosion is its job description. It is not armor that deflects. It is armor that dies professionally, one layer at a time, for 20 years. Now price it. A shield like that, sized for a crude hull, meters thick across a face wide enough to shadow a habitat, comes out in the hundreds of tons at minimum, and serious studies of crude interstellar concepts have priced forward shielding in the thousands of tons. Let me be generous tonight, the way I was generous with the 1-ton can. Call it 400 tons of shield for a small crude vehicle. 400 tons. Write it on the whiteboard. And now watch the whiteboard fight back. Because this is the moment the whole night folds in on itself. That shield is mass. And mass is the one substance the rocket equation feeds on. Every ton of shield must be accelerated to cruising speed along with the ship. And back in Chapter 5, you watched what acceleration costs. The bill is not linear. It multiplies. So 400 tons of shield does not add 400 tons of fuel. It adds thousands of tons of fuel. And here is the turn of the screw. That new fuel is itself mass, riding at the front of the fuel line for years. And the tanks that hold it enlarge the ship. And the enlarged ship presents a wider face to the interstellar beam. And a wider face needs a wider shield. And the wider shield is heavier. And the heavier shield needs more fuel. Around it goes. Shield demands fuel. Fuel demands tankage. Tankage widens the ship. The wider ship demands more shield. This is not a difficulty. Difficulties get solved. This is a feedback loop, a circle with no exit drawn anywhere on it. And every crude starship design in the literature has been caught inside this circle, walking it like a prisoner walking a yard. And the loop has a second gear, because speed sits inside it too. Every impact energy from last chapter scales with the square of velocity. So fly faster, and the beam hits harder, which demands more shield, which demands more fuel, which, and I want you to catch the full cruelty of this, is fuel you are burning in order to go faster, which makes the beam hit harder still. The two great walls of this night, the equation and the dust, are not separate walls. They hold hands. Your engine problem makes your armor problem worse. And your armor problem makes your engine problem worse. And the harder you push on either one, the harder both push back. Could you cheat instead of armoring? People have tried, on paper, for 50 years. And I will give the cheats their due, because some are clever. Fly a disposable dust catcher kilometers ahead of the ship. A sacrificial wall on a leash. And let it take the hits. Now you are accelerating two vehicles, and the catcher erodes and must be replaced from stores, which is mass. Vaporize incoming grains with a laser. A point defense gun for specks of soot. The grains arrive at 60,000 kilometers per second, giving your targeting computer milliseconds against something the size of a bacterium, and the laser and its power plant weigh tons. And every watt of that power plant is heat the ship must dump. And hold that thought about heat, because it grows into its own wall very soon. Steer a magnetic field ahead of the bow and deflect the incoming rain. The protons bend. but dust grains are mostly neutral, uncharged. Deaf to magnetism. So the field catches the drizzle and lets the grenade straight through. Every cheat, priced honestly, either fails the hard cases or pays its bill in the same currency. Mass. The one currency this ship cannot spend without the equation noticing. So step back and look at the whiteboard, because Act 2 of this story is over, and the drawing tells its own history. We began with a 1-ton can and a simple wish. One human. One lifetime. Out. Every engine we hired made the ship bigger. Every wall we hit made it bigger still. Starshot escaped the equation entirely by shrinking the traveler to a postage stamp. And the moment we insisted on people, the vacuum turned hostile, and the armor against it dragged us into a circle that eats designs whole. Every solution has arrived, carrying the next problem in its luggage. That is the pattern of this night. And by the end you will see it is the whole answer to the question in the title. But I can hear the objection, because it is the right objection, and I have been waiting all night for you to make it. Every wall so far has been an engine wall, or a fuel wall, or an armor wall. Hardware, and hardware surrenders eventually. Give the species 500 years instead of 50. Let the engineers iterate, and surely the loop cracks. Fine. Fine. Let us find out. Because Act 3 begins with a gift. I am going to hand you the impossible. Free of charge. A perfect engine. As good as physics allows. Fuel beyond counting. A shield of whatever mass you like. And the power to push it. Every wall from tonight. Demolished by decree. The ship flies. The crew boards. The voyage begins. And what I'm going to show you next is that the ship still fails. And it fails somewhere no engine can reach. Because the deadliest cargo this vessel carries was never the fuel. It is the heat, then the years, then us. So the gift is on the table. A perfect engine. Unlimited fuel. A shield of any size. The ship flies. And within hours of the engine lighting, the crew is fighting for their lives against an enemy nobody at the press conference ever mentions. The ship is cooking itself. I know how that sounds. Because everyone knows space is cold. Ask anyone. Space is the coldest thing there is. A few degrees above absolute zero. Cold enough to freeze air itself. Drop a warm object into deep space, and your instincts say it should freeze solid in minutes. The way you would on a winter mountain. And your instincts are wrong, because they learned everything they know inside an atmosphere. Here is the piece of physics your body never had a chance to learn. On Earth, heat leaves you 3 ways. It conducts into whatever you touch. It rides away on moving air. And it radiates off you as invisible light. On a cold day, the first 2 do almost all the work. The air steals your warmth, and the wind steals it faster. And that theft is what cold means to a human being. Now step into vacuum. There is nothing to touch. So conduction is gone. There is no air. So convection is gone. Of the 3 exits, 2 are bricked shut, and the only one left is radiation, the slowest and weakest of the 3. A vacuum is the best insulation in the universe. It is the exact principle of a thermos bottle, and this is the joke physics plays on every spacecraft ever built. Space is freezing cold, and it wraps your ship in the world's most perfect blanket. The sun does not have this problem. Nothing in nature does, because nothing in nature minds running hot. Your ship minds. Inside that hull is machinery, holding a bubble of springtime for the crew. and every watt of power that machinery uses becomes heat. And the heat has nowhere to go. Count the sources with me, because they never stop. The life support system, pumping and filtering around the clock. Heat. The computers. Heat. The lights that grow the food. Heat. And the crew themselves. Each human body, a steady 100-watt space heater that runs for a lifetime and cannot be switched off. And towering over all of it, the gift itself. That perfect engine at the back of the ship is channeling energies that embarrass power grids. And no machine ever built is perfectly clean. Even at efficiencies engineers dream about, a starship drive leaks a fraction of its power as waste heat into its own structure. And a fraction of a civilization-sized number is itself a monstrous number. The better your engine, the bigger your furnace. Seal all that inside a thermos, and the arithmetic is short. The temperature climbs. It climbs through comfort, past survival, toward oven. And the ship does not need to hit anything or run out of anything to die. It just needs to keep working. A starship that generates heat faster than it sheds heat is a slow explosion with a crew inside. And every single one of them does generate it faster, until you build the way out. The way out is the radiator. And radiators are why real spacecraft look the way they do. You run fluid past every hot machine, collect the heat, pump it to enormous thin panels facing the dark, and let those panels glow it away as infrared light. The only exit vacuum left open, the International Space Station, which runs on about 100 kilowatts, roughly the power of a nice car, needs radiator wings the size of tennis courts just to keep a 6-person crew from stewing. That is the exchange rate at 100 kilowatts. Our ship is not running 100 kilowatt. Our ship, with its gifted engine and its shielded hull and its farms and factories for a crew of hundreds, runs power levels millions of times beyond the station. And the radiators scale with it. Priced honestly, a crude starship's heat rejection system comes out as acres of paneling, square kilometers of thin, glowing surface, a metal forest of wings larger than the ship they serve. In most serious designs for high-powered vessels, the radiator is the single biggest thing on the drawing, and the vehicle underneath looks like an afterthought bolted to its own cooling system. By now you can hear the equation clearing its throat, so I will keep this short. The radiators are hundreds of tons, and you know what tonnage costs. But this wall has a private cruelty the others lacked. Radiators only work as wide open area. Acres of thin, delicate panels spread naked to space. And area is exactly what Chapter 9 taught us, never to show the interstellar medium. Every square meter of radiator is a square meter of target. The dust that our meter's thick bow shield exists to stop now has a tennis court complex of tissue paper riding alongside the hull. Unarmorable, by definition. Because armor an emitter, and it stops emitting. Fold the panels behind the shield and the ship cooks. Spread them wide, and the sandblaster goes to work on your cooling system for decades. A starship with failed radiators does not limp. It bakes. But notice what just changed in the story, because it is bigger than the radiators. This wall was different in kind. The equation, the energy cliff, the dust. Those were walls about going fast. This one never mentioned speed. This was a wall about staying alive while the machine runs. And it was only the first of them. Because the moment we gave you the perfect engine, the enemy stopped being velocity. The enemy now is time. 50 years of pumps that cannot stop pumping. Panels that cannot stop glowing. Machines that cannot stop working. With no port, no factory, and no help within 4 light years. Which brings us to the quietest wall of the night, and the one I find genuinely frightening. Here is a question no brochure about starships has ever answered. Forget reaching the stars. What is the longest any machine has ever simply worked? Not survived. Worked. Your car needs a mechanic every year. A jet engine gets torn down and rebuilt on a fixed schedule measured in thousands of hours. A nuclear submarine, one of the most reliable machines our species produces, comes home to a shipyard every few years and gets swarmed by specialists. Power plants shut down for maintenance. Bridges get repainted and rebolted. Everything you have ever trusted your life to sits inside a vast, invisible web of factories. Spare parts, inspectors, and repairmen. And the machine you trust is really the web you trust. A starship leaves the web. That is the entire specification. Stated plainly, the moment the engine lights, the nearest factory is behind you, receding at thousands of kilometers per second. Whatever breaks, and across 50 years, everything tries to break, gets fixed by the crew. From stores, with knowledge they carry in their heads, or it stays broken forever. There are no rescue missions in this story. No rescue vehicle built alongside your ship could reach you in time to matter, because it would be chasing you across light years at the same class of speed, arriving years after whatever emergency called for it. Now let me show you what 50 years without the web actually looks like. And I do not need fiction to do it, because we are running the experiment right now. 2 experiments, actually, and you have already met them both tonight. The first is the International Space Station, and it is the sobering one. The station is the most carefully maintained machine in existence. It flies 400 kilometers overhead, minutes from Earth, fed by a supply chain of rockets bringing fresh parts, fresh filters, fresh water, and fresh humans on a constant schedule. And even with all of that, the station is a full-time repair job. Ask the astronauts. Their weeks fill with maintenance, replacing pumps, patching seals, chasing air leaks, swapping failed components flown up from factories on the ground. In recent years, as the station has aged past 25, cracks have appeared in a Russian module and the leaks have become a standing agenda item. 25 years old, wrapped in the best support web ever built. And the machine is showing its age everywhere. Our starship must run twice that long, with the web amputated at launch. The second experiment is Voyager. And now I am collecting the debt from Chapter 1, because I told you every piece of that story would matter tonight. Voyager 1 is the best case in history. It is the single most reliable complex machine human beings have ever built, engineered by a generation at the absolute peak of its craft, and it has flown for 47 years, which is, notice, almost exactly the length of our mission. So Voyager is the experiment. Voyager is what 50 years alone actually does to a machine. And the verdict came back in November of 2023. One chip died. One small slab of 1970s memory, cooked slowly by 46 years of radiation, and the most reliable machine in history started speaking gibberish. And the fix. Remember the fix. Because the fix is the frightening part. The fix was archaeology. The people who designed that computer were retired or dead. The team in Pasadena dug decades-old schematics out of storage boxes, called elderly engineers at home, and rebuilt an understanding of their own spacecraft from paper and living memory. And it took months, and they had a luxury our starship crew will never have. The entire knowledge of Earth was a phone call away. now board our ship and run the same failure. Year 46 of the voyage. A critical component dies. Something deep in the reactor control system, or the life support plumbing, and the crew pulls up the documentation. Who wrote that documentation? Engineers back in the solar system. Some of them dead by now. All of them unreachable. Because at this distance, a radio question takes years to arrive and years to return. Who aboard understands this component? Whoever was trained on it, and here the floor opens up. Because the people who boarded at launch, the ones who watched the ship being built, who knew why every valve was placed where it was placed, those people are in their 80s, or in the ship's cemetery. The crew fixing the machine in year 46 is not the crew that learned the machine. It is their students, or their students' students, working from notes. And every engineer watching this video just flinched. Because everyone who has ever inherited a colleague's undocumented work knows exactly what those notes are worth. This is the woe. So let me give it its true name. Knowledge is a ship system. It corrodes like one. It fails like one. On a voyage longer than a career, the understanding of the ship must be maintained just like the hull, transferred from person to person across decades without loss. And there is no material in the universe harder to preserve, because it evaporates a little at every handover and it dies completely, without warning, every single time its last holder does. Voyager lost knowledge with a whole planet of universities underneath it. Our ship loses it in an aluminum can, alone, at a fraction of light speed. And even with perfect knowledge, there is the arithmetic of the parts themselves. And I want you to see this number, because reliability is a numbers game, and the numbers here are silent and merciless. A vehicle of this complexity carries millions of components: pumps, valves, sensors, boards, seals, welds. Suppose each one is magnificent, a piece so well made that in any given year it has only one chance in 10,000 of failing. That is aerospace-grade excellence. Now run 1,000,000 of them for a year, and excellence hands you about 100 failures. Every year, 2 failures a week, every week. For 50 years, most of them trivial, some of them not, and the crew never knows which kind is coming. A starship is a machine that must repair itself faster than it dies, forever. And the mathematics guarantees that the dying never pauses. So the ship answers the only way a ship can. It brings the web along, a machine shop, raw metal stock and printers and forges, spare parts. Not a shelf of them, warehouses of them. Tons upon tons of dead weight riding along for decades against the day one specific valve gives out. Cut the spares to save weight, and you are betting lives on nothing failing. Carry them, and the old wheel turns again. Every previous wall has followed us aboard. Here is where Act 3 stands. Then, we gave the ship a perfect engine, and the ship replied that the engine was never the hard part. Keeping a machine alive for 50 years without Earth is the hard part. And the machine defends itself with mass, with workshops, with libraries, and with an unbroken chain of teaching that must not slip once between generations. And I have been holding one word back all chapter. And you noticed, every problem so far assumed the finest crew imaginable. Healthy, trained, and alive. Next chapter. We open the crew cabin, and I have to tell you what is actually inside. Because the most fragile component on this entire vessel, the one with the shortest service life, the strictest operating conditions, and the least tolerance for failure, has never been the chip or the pump or the radiator panel. It is the 70 kilograms of salt water and bones sitting in the pilot's chair. And physics has been trying to kill it since the moment the engine lit. Every machine we have discussed tonight came with a specification sheet. So let us be fair and write one for the crew. Because the crew is equipment too. This is the payload the entire mission exists to deliver. And here is what it demands. Operating temperature. A narrow band around 20 degrees. Atmosphere. A precise oxygen mix. Delivered continuously. No interruptions longer than 3 minutes. Fuel. 0.5 kilogram of food and a few liters of water per unit per day. Every day. For 50 years. The units self-repair, which is miraculous, and self-replace, which no machine can match. And then the sheet reaches 2 line items that no engineer can cross out. And those 2 items are this chapter. Because one of them we can barely afford, and the other we cannot ship at all. The first is radiation shielding. And to understand the requirement, you have to understand something almost nobody outside the field appreciate. You have never lived a day outside Earth's armor. This planet is a fortress. A magnetic field the size of a world deflects the worst of what space throws. And above your head sits an atmosphere whose protective bulk is equivalent to standing under 10 meters of water. Every human who ever lived, every astronaut included, spent their existence inside or barely above that armor. The station crews still fly within the magnetic walls. Only a few dozen humans ever stepped fully outside. And the longest any of them stayed out was 12 days. Our crew steps outside for 50 years, and what waits out there comes in 2 forms. The first is weather, the sun, and every star occasionally erupts, throwing storms of charged particles across space. And a bad solar storm delivers doses that cause radiation sickness or death in unshielded humans within hours. Weather, at least, can be forecast and survived. The crew retreating into an armored storm shelter at the ship's core. Waiting it out the way, sailors ride out a hurricane. The second form has no forecast and no end. It is called galactic cosmic radiation, and it is the ocean itself. A thin, eternal rain of atomic nuclei accelerated to enormous energies by exploding stars across the galaxy, arriving from every direction. Always. These are not gentle particles. They are cannonballs. Some of them heavy nuclei like iron moving near light speed. And when one crosses a human body, it does not tap. It drills, snapping DNA strands along a track of shattered molecules. And here is the engineering horror. Throwing a little metal at the problem can backfire. A cosmic ray striking a thin aluminum wall can shatter into a spray of secondary particles. One cannonball becoming shrapnel. So simply wrapping the cabin in more hull is not automatically an improvement. And sometimes it is the opposite. Stopping these things honestly takes bulk. Meters of water or plastic or rock. Tons of it wrapped around every space where humans live. And the old wheel turns once more. Because you know by now what tonnage costs this ship. Skimp on the bulk. And the crew absorbs, year after year, a dose that steadily raises cancer rates, damages hearts, and clouds nervous systems. NASA's own career limits for astronaut exposure would be spent within the first years of this voyage. The rest is debt. The second line item is stranger, because the missing ingredient is not a substance at all. It is a direction. Down. The crew needs down. Gravity is not scenery. It is an input. And every system in your body was engineered against it across 4 billion years. Remove it, And the body does something terrifyingly sensible. It begins dismantling what it no longer needs. And we know this precisely because we ran the experiment. And this is where I bring in the twins. Scott and Mark Kelly are identical twin brothers, and both became NASA astronauts, which handed science a gift it could never have manufactured. Two genetically matched humans. One control group with a pulse. In March of 2015, Scott launched to the station for 340 days, the longest single American spaceflight, while Mark stayed on Earth. Same genes. 1 year. 2 planets worth of difference. And NASA ran 10 research teams over both men. Before, during, and after. What weightlessness did to Scott in under 1 year, measured against his own twin, reads like an inventory of quiet demolition. Bone dissolving, the skeleton shedding density every month at rates that would horrify a physician treating osteoporosis, because the body reads a floating skeleton as surplus. Muscle wasting despite 2 hours of daily mandatory exercise. The heart itself deconditioning. Since pumping blood in free fall is easy work, and the heart, like any muscle, downsizes to match its job. Floats, shifting headward without gravity to hold them low, congesting the skull, and pressing, many researchers believe, on the backs of the eyes, because Scott, like most long-duration astronauts, came home with measurably changed vision. And some astronauts never fully recover theirs. Gene expression shifted. The chemical caps on his chromosomes changed length. Immune function wobbled. And months after landing, some markers had still not returned to baseline. 340 days, inside Earth's magnetic armor, with fresh supplies arriving regularly, and a planet 19 minutes below by escape capsule. That is the best case. And our mission multiplies its duration by 50, and deletes the armor, the resupply, and the exit. So the ship must manufacture down. And physics does offer exactly one honest way. Spin. Rotate the crew section and centrifugal force presses bodies outward against the floor. Artificial gravity. Real enough for bones. The physics is Newton. Ancient and certain. And the engineering is another heavy invoice. Because spin only feels like Earth if the radius is generous. Spin a small ring fast, and the inner ear rebels. Every head turn triggering vertigo. So, a comfortable one. Gravity ring wants a radius of hundreds of meters, which means our vessel now carries a rotating structure the better part of a kilometer across. Massive. Spinning for decades on bearings that cannot be replaced. Holding pressure seals between spinning and stationary sections for 50 years. Step back and look at the drawing now. A meters-thick shield at the bow. Radiator wings like a glowing forest. Warehouses of spares. A machine shop. Meters of radiation bulk around the living spaces. And now, a spinning ring the size of a small stadium. The 1-ton can is a city block. And every single addition exists to keep the payload from dying of the voyage itself. And even now, with every system drawn, the specification sheet has one last line, and it is the one that breaks the whole design philosophy of everything humanity has ever launched. Service life of the payload, roughly 80 years, and the mission needs the payload functional at arrival. Because 50 years is a career, it is most of a life, and the moment a voyage stretches toward the length of the humans flying it. A door opens at the back of the ship that no engineer wants to walk through, because on the other side of that door, the passenger manifest stops being a list of names. It becomes a family tree, everything tonight. Every gift I have handed you has protected one number, 50 years, one working lifetime. The crew that leaves is the crew that arrives. And I have to tell you now that the number was always a bluff. And it is time to call it. Look at what the bluff assumed. 50 years to cross the driveway assumed 3% of light speed. 50 years to Alpha Centauri assumed 10%. Sustained, with a way to stop at the far end. And you have now watched what speed costs. The energy cliff, the dust turning to gunfire, the shield feeding the equation. Every one of those walls grows taller with the square of velocity, and every honest design response we found tonight pushed the crew's speed down, not up. Daedalus, unmanned, no brakes, no shield worth the name, bought 12% by burning a planet's decades of energy. A crude vessel, armored, shielded, spinning, cooled, and stocked for arrival. Prices out slower. Run the full stack honestly at 1 or 2% of light speed, and the driveway alone swells past a century. Alpha Centauri sits at 400 years, and the arithmetic of the crew collapses in a single sentence. The people who board this ship will not see the destination. Their great-great-great-grandchildren might. Engineers call the answer a generation ship, a vessel whose crew lives, works, raises children, grows old, and dies aboard, handing the mission to heirs, for as many human lifetimes as the crossing takes. And I want to walk through what that actually requires. Because the phrase slides past too easily, I am going to stay out of the sociology, the politics of a sealed town, the question of what its people believe in by year 300. The engineering constraints are heavy enough on their own, and the first one arrives before launch. In an office, with a spreadsheet, somebody has to decide how many people board, and the spreadsheet fights itself. Small crews save mass, and mass is the currency every wall tonight gets paid in. So the equation votes for dozens. Biology votes against. Loudly. Because a small founding population breeds inward. Generation after generation, inside the same closed gene pool. And inbreeding is not a stigma. It is mathematics. Recessive disorders surfacing. Resilience draining. Until the crew's own chromosomes become a ship system in slow failure. Population geneticists have run this exact problem for interstellar voyages, and the published answers span a range, from studies arguing that around 100 to 200 carefully managed people could hold the line, to models of multi-century crossings that call for thousands, with the honest answer depending on mission length, reproductive rules, and how much risk you are willing to load onto your descendants. Some researchers argue a smaller crew works if you ship frozen sperm and eggs as genetic cargo, a library of unborn diversity in a freezer. And notice what every version of the answer has in common: the freezer, the larger habitat, the extra souls. All of it lands on the same scale, the shield and the spares landed on, and the needle moves the same direction every time. So call the founding crew hundreds, and immediately the ship changes species again, because hundreds of people across centuries need what hundreds of people have always needed: a hospital, and not a first aid station, a surgical suite with imaging, and a pharmacy that manufactures drugs, because no stockpile of medicine survives 4 centuries of shelf life, a school, running continuously for the entire voyage. And hold that thought, because the school is about to become the most important system aboard. Farms, air, water, an entire living metabolism that I am saving for its own chapter, because it deserves one. Workshops, laboratories, a morgue, nurseries. The vessel is no longer a vehicle carrying passengers. It is a sealed town of hundreds, moving at thousands of kilometers per second, that must function longer than most nations have existed. And now stack the two clocks tonight has built, side by side, because this is where the generation ship shows you its true face. Clock 1. From Chapter 12. Machines fail relentlessly. The mathematics of a million components guarantees a drumbeat of breakdowns forever, and the ship survives only through constant skilled repair. Clock 2. This chapter, the skilled repairers die. Every engineer who boards, every physician, every navigator, is gone within decades, and the mission runs for centuries. So the ship must do something no vessel has ever done. It must grow its own crew. From children born aboard, continuously, without one failed handover, for the entire crossing. Sit with what the school on this ship actually is. It is the transfer of an entire technological civilization's working knowledge. Reactor physics, surgery, orbital mechanics, chemistry, agriculture, welding, through a population of a few hundred, hand to hand, for 400 years, where the students have never seen the sky, never met the designers, and must master systems built by people 4 generations dead. From documentation those people left behind, you watched Earth's finest institution, with a planet of universities behind it, spend months rediscovering how its own 46-year-old spacecraft worked, because the knowledge had retired and died. That was one chip, on one machine, with every expert alive, a phone call away at launch. Now run that failure mode across every system on a sealed town. For centuries, where the only experts who will ever exist are the ones the town itself teaches. This is the wall that makes the generation ship different in kind from everything before it. The equation, the dust, the heat, those were physics. And physics at least holds still while you engineer against it. A generation ship bets the mission on an unbroken chain of teaching, hundreds of links long, where every link is a human being who must choose, in a town they never chose to be born into, to spend their one life maintaining a machine so that people they will never meet can someday step off it. The founders sign up as volunteers. Every soul after them is born aboard, and the mission simply assumes their competence. For 4 centuries, sight unseen, can a sealed town of hundreds hold a civilization's knowledge together for 400 years? Nothing in human history answers yes. Nothing answers no. It has simply never been tried. And there is no test for it, because the test is the voyage. But before any of that, before the school and the handovers and the 400 years, the town has to solve a problem so basic it sounds like a joke. And I promise you, it is the deadliest system on the ship. The town has to breathe. Air does not come in tanks. Not for centuries. Not for hundreds of lungs. Air has to be grown, recycled, resurrected endlessly by a living machine of plants and microbes and chemistry sealed inside the hull. An artificial biosphere. And here is why my voice just changed. Everything else tonight, we have never tested. This one, we tested. We built the sealed world. We sealed 8 humans inside it. It was 1991. It was in the Arizona desert. It cost $200 million. And what happened in there is the single most important experiment ever run on the future of our species in space. The air began to disappear, and for 16 months, nobody could find where it was going. Drive an hour north of Tucson, Arizona, and you will find a glass cathedral standing in the desert. 3 acres of white steel frame and windows, pyramids and domes glittering in the heat, looking like a city from a better future that somehow landed in the sagebrush. It is called Biosphere 2. The name is a tribute, because Biosphere 1 is the Earth. And in 1991, it was the site of the boldest biological experiment of the 20th century. The question it asked is the exact question our starship just asked. Can human beings build a sealed world that keeps them alive, not a submarine with air tanks? Not a station fed by supply rockets. A genuine miniature Earth, closed to matter, where every breath, every meal, and every drop of water is grown, cycled, and resurrected inside the walls, forever, by a living machine. They did not build a cautious version. Inside those 3 acres, the designers packed a rainforest with real trees, a savanna, a mangrove marsh, a desert, a farm, and an ocean, an actual ocean, holding nearly 4 million liters of salt water with a living coral reef and a wave machine, around 4,000 species of plants, animals, and insects were selected and installed. A Noah's Ark, curated by ecologists. The engineering underneath was just as serious. The structure was sealed tighter than any building ever constructed, leaking less air in a year than a typical home leaks in a day. And because sealed air expands and contracts with the desert temperature, the designers gave the building a pair of mechanical lungs. Vast underground chambers with flexible rubber diaphragms that rose and fell so the glass would not shatter as the world inside breathed. $200 million. Years of design by capable engineers and ecologists. Every number checked. On paper. The cycles closed. The plants would make the oxygen. The crops would make the food. The microbes would turn waste back into soil. And the water would rain from the cooling coils onto the rainforest and run down to the ocean and around again. On September 26, 1991, 8 people in jumpsuits waved to a crowd, stepped through an airlock, and sealed the door behind them for a planned 2 years. And I want to be fair to what they achieved, because the crew was tough and serious. They farmed like pioneers, raising crops, goats, chickens, and pigs on half an acre. They ran the machinery of a small world. They were hungry most of the time. The farm never quite delivered the calories the plan promised, and they kept going anyway, growing over 80% of everything they ate for 2 full years. But the world itself, the sealed miniature Earth, began to fail them in a way nobody predicted, and the failure is the reason this chapter exists. The oxygen started to vanish. Earth's atmosphere, and the air sealed inside on closing day, holds about 21% oxygen. Month by month, the sensors inside Biosphere 2 watched that number slide. 20%, 19, 18. The decline was slow, relentless, and completely unexplained. The crew and the scientists outside checked the obvious suspects, and the obvious suspects came back innocent. And the number kept falling, month after month, for 16 months, while the 8 people inside effectively climbed a mountain without moving, the air thinning around them as if the building itself were inhaling their oxygen and giving nothing back. By January of 1993, the level had fallen past 14.5%, the equivalent of living at well over 4,000 meters of altitude. Crew members were dragging themselves through their farm work, stopping for breath on staircases, and some began waking at night gasping, their bodies jolting them awake because breathing had become shallow enough to matter. The managers faced a choice between the purity of the experiment and the safety of the crew. And they chose the crew. Tanker trucks arrived through the desert, and pure oxygen was pumped into the sealed world from outside. The crew stayed, finished their full 2 years, and came out lighter and tougher. And the question everyone wanted answered was where the air had gone. The answer took time to nail down, and it is my favorite scientific detective story of that decade, because the thief turned out to be hiding in 2 places at once, and neither one was on anybody's suspect list. The first culprit was the soil. The designers wanted a lush, productive world, so they filled the farm and forests with rich soil, heavy with organic matter. Rich soil is not dirt. It is a living continent of microbes, and microbes breathe exactly the way we do, consuming oxygen and exhaling carbon dioxide. Given all that food, the microbial population exploded, and the soil of the little world began breathing harder than its plants and people combined. Billions of invisible lungs pulling oxygen out of the sealed air day and night, which only deepened the mystery. Because if microbes were burning the oxygen, the carbon dioxide should have skyrocketed, and it had not risen anywhere near enough. Oxygen was leaving, but the exhaled carbon was disappearing too. Matter does not vanish. Something in the building was eating the exhale. The something was the building. Biosphere 2 contained over 100,000 tons of exposed structural concrete. And concrete is chemically alive. It contains calcium hydroxide, which reacts with carbon dioxide in the air, pulling it in and locking it away as calcium carbonate. Limestone, forming inside the walls. The microbes stole the oxygen and exhaled it as carbon dioxide. And then the walls of the world ate the carbon dioxide and turned it to stone. The atmosphere was not leaking out of the building. The atmosphere was being fossilized into the building, breath by breath. And no ecologist on Earth had thought to model the concrete as a species. That is the lesson. And it is worth saying slowly, because it is the most important sentence in this act. The system was designed by excellent people, with a $200 million budget, on the surface of the only planet known to support life, with rescue trucks an hour away. And it was betrayed by a chemical side effect of its own architecture that nobody predicted, discovered only after 16 months of continuous mystery. Closed ecosystems fail sideways. They do not fail where you reinforce them. They fail in the coupling between 2 things you never thought to couple: soil, bacteria, and structural concrete. And the only way anyone has ever found such failures is by living inside them while they happen. Now lift this whole story onto our starship and feel the temperature drop. Our sealed town of hundreds needs exactly this machine. A closed biosphere. Air and food and water resurrected endlessly by biology and chemistry in a can. The most ambitious, full-scale attempt our species has ever made needed emergency oxygen from outside after 16 months. On Earth, with gravity, sunshine, a stable temperature regime, and the full scientific establishment watching through the glass, the Starship version must run for centuries. Under spin, bathed in radiation that mutates its microbes, sealed inside a hull whose every material is a potential secret chemical actor, with no tanker trucks, no outside atmosphere, and no second biosphere to retreat to when the Starship's oxygen graph starts sliding. and Biosphere 2 says it will. The crew gets to be the detectives, the suspects, and the victims, all at once. And the case must be solved before the air runs out. Every single time it happens, for 400 years. And with that, the ship on our whiteboard is finished. So stand back with me and look at it. A shield of hundreds of tons at the bow, radiator wings by the square kilometer, warehouses of spares and a machine shop, meters of radiation bulk around the living decks, a spinning ring the better part of a kilometer across, a hospital, a school, farms, and a sealed biosphere for a town of hundreds, plus the fuel to push all of it, and the tanks to hold the fuel, and the shield to cover the tanks, priced honestly. The vessel runs from hundreds of thousands of tons toward millions. A floating city, the largest object humanity would ever have constructed, and every single ton of it exists for one reason only: to keep the payload alive long enough to arrive. Which is when you should notice the word I just used. Arrive. Because through this entire night, through every wall and every invoice, I have quietly let all of us assume that if the ship survives the crossing, the story ends. It is time to confess that this assumption is false. And the reason it is false is my favorite twist in the entire problem. There is one more wall, standing at the far end of the voyage, in the dark, past the last gram of fuel, and it has been waiting there since the first chapter, getting out of a solar system. It turns out, was always the cheap half of the trip. The expensive half is stopping at the next one. There is a joke as old as flight itself, and every pilot knows some version of it. Takeoff is optional. Landing is mandatory. Tonight, at the far end of a 400-year voyage, that joke stops being funny, because here is the physical truth underneath it. Leaving is free. In one specific sense, once you are moving, the universe never charges you again. A ship that escapes the sun's grip will coast forever. No fuel, no effort. Newton's first law riding shotgun for eternity. Voyager will cross the galaxy for billions of years on the push it got before 1980. Escaping only requires speed. And speed, once bought, is yours. Arriving is the opposite of all that. Arriving means giving the speed back. Every kilometer per second you purchased with fuel and fire on the way out must be surrendered at the destination. Deliberately, precisely, and paid for a second time. Because a ship that reaches Alpha Centauri at cruising velocity does not visit Alpha Centauri. It streaks through it at 10% of light speed. The crossing from one side of that entire star system to the other takes a few days. The target planet flashes past in hours. And then the stars you spent centuries reaching are shrinking behind you. Forever. While your ship continues into the dark, carrying its town of living heirs toward nothing, with no third stop on any map. Remember the promise in the opening. Leaving means living, people. Going and staying gone. Somewhere. A voyage that cannot stop is not a voyage. It is an exile with scenery. So breaking is not a feature of the mission. Breaking is half the mission. And I can prove it with the cruelest symmetry in tonight's whole story. Think back to Chapter 5, to the rocket equation and its compounding interest. The equation charges you for every change in velocity, and it does not know or care which direction the change points. Speeding up from 0 to cruise, and slowing down from cruise to 0, are the same size purchase, which means the fuel to stop at the far end must be carried the entire way. And here, the compounding turns vicious. because that braking fuel is cargo for 400 years. Dead mass that the departure burn must accelerate, and accelerating it demands more departure fuel, which demands bigger tanks, which demand more shield. Adding the ability to stop does not add to the ship. It multiplies the ship. The pub engineers of Daedalus saw this exact multiplication, ran the numbers on braking, watched their 54,000-ton vehicle balloon toward the absurd, and made the only honest choice available, which is why their masterpiece was a flyby that waved as it passed. And if you are now thinking what half the room always thinks, that the answer is the starshot trick in reverse. Leave the engine at the destination. Let a laser catch the ship. Then follow that thought one step further. Because it is a good thought with a hole in the middle. A braking laser at Alpha Centauri must be built at Alpha Centauri. Before you arrive. By somebody already there. There is nobody already there. The entire reason for the voyage is that nobody is there. And you cannot mail construction equipment ahead without first solving the identical braking problem for the construction equipment. The trick that launches a ship cannot catch one. And even Starshot itself, the boldest interstellar plan our species has funded, surrenders to this war completely. Their postage stamp reaches Alpha Centauri in 20 years and does not even slow down. It crosses the whole system in hours, cameras blazing, and continues into interstellar night forever. The most advanced starflight concept on Earth is, by design, a beautiful bullet that never stops. For a camera, that is a triumph. For a town of 400 humans, it is a hearse. Physics does offer exactly one honest discount at the far end, and I want to give it to you. Because it is elegant and it is real, and our own engineers already use its little brother. The destination has a star, and stars push back. Sunlight itself presses on everything it touches. So, a vast reflective sail, unfurled on approach, could ride the target star's own light like a headwind, bleeding off speed without burning a gram. Stars also have gravity, and a ship can swing close and trade velocity in a gravitational handshake. The same trick our probes have played on Jupiter for 50 years. Researchers have designed exactly such arrivals. Sail first plunges past a bright star, using light and gravity as brakes that never run empty. And the discount comes with a merciless condition printed underneath. Light pressure is gentle, so the sail must be enormous, tens of kilometers across, and the pass must run close to the fire. And above all, the arriving ship must be light. The published designs that make starlight braking close their equations are probes of grams and ton. Our vessel mass is hundreds of thousands of tons, wrapped around a shield, a spinning ring, and a biosphere, and against inertia like that. A star's light is a whisper against a freight train. The discount is real. Our ship cannot fit through the door to claim it. So stand at the whiteboard one last time and watch what this wall does to the voyage. Because it reaches backward through everything we built. The braking burn must roughly match the departure burn. So the fuel doubles, and the tanks double, and the shield widens to cover them, and the whole pile compounds one more time. And the ship that was already the largest object in human history now dwarfs its own earlier self. Or else the cruise speed falls again, and the 400-year crossing stretches toward 600, toward 800, and every added century runs the biosphere longer, the schools longer, the unbroken chain of teaching longer, another dozen generations of children born aboard a town that must not fail once. Every wall of this night, the equation, the energy, the dust, the heat, The failures, the bodies, the generations, the air. All of it was the price of going. This wall stands at the end and quietly doubles the check. And there is no version of the mission that skips it. That is the last wall. There are no more after this one. And I promised you at the start of tonight that the ship would fail somewhere unexpected. So, in the next chapter, we are going to do what engineers do at the end of a failed design review. We are going to lay every invoice on the table, add up what leaving the solar system actually costs. All of it, at once, and look honestly at the total, because the total is the answer to the question in the title, and it is not the answer anyone came here expecting. Every failed engineering project ends the same way. In a quiet room, with the invoices spread across a table, and somebody senior enough to be honest saying out loud what the pile actually means. Tonight that room is ours. So let us lay the whole night on the table and read it back cold. Because when you see the invoices side by side, they stop being separate problems and become a single shape. We started with a 1-ton can and a simple wish. One human, one lifetime, out of the solar system. Chemistry answered first, and its price was a fuel tank outweighing the observable universe. So we fired chemistry. The nucleus answered next, and the nucleus genuinely works. Orion could have flown on the bombs of its own decade, and it lost its future at a signing table. Because the first wall was never physics alone. Fusion closed the arithmetic for a robot, and the invoice was 54,000 tons. A mining industry floating in the clouds of Jupiter, and 30 years of humanity's entire energy output for a flyby that waves as it passes. Starshot escaped the equation completely by leaving the engine on the ground. And the price of that genius was the payload. A few grams. A camera. No crew. No brakes. A beautiful bullet. Then we insisted on people. And the invoices changed character. The vacuum turned into a particle beam and demanded a shield. And the shield fed the equation. The machinery demanded radiators, and the radiators spread acres of tissue paper through the sandblaster. 50 years without a repair web demanded warehouses, workshops, and an unbroken chain of human knowledge. And Voyager showed us what happens to knowledge after 46 years. On a mission with a whole planet of libraries, one phone call away. The human body demanded meters of radiation bulk and a spinning ring half a kilometer wide. Because bones dissolve in freefall and cosmic rays drill DNA, the honest crew's speed fell. The voyage stretched past a single life. The crew became a town. The town demanded a biosphere, and the only sealed biosphere our species ever built needed rescue oxygen after 16 months. On Earth, with the trucks an hour away, and at the far end of everything, the destination presented the final invoice, because stopping costs what starting cost, carried the whole way, compounded by the equation, doubling the ship one last time. Look at the pattern across every page, because it is the same pattern every time. Mass demands energy. Energy demands fuel. Fuel is mass. Speed makes the vacuum lethal. Armor against the vacuum is mass. Mass pulls the speed back down, and lost speed stretches the voyage. And a stretched voyage demands generations, and generations demand a living world aboard. And a living world is mass. There is no weak link in that chain to attack. And that is the discovery of the night. Every link is load-bearing. Every link is welded to its neighbors, and pulling on any one of them tightens all the others. Now, I promised you honesty in both directions. So here is the other side of the ledger. Stated plainly and without a wink. Nothing tonight broke a law of physics. Read that again. Because it matters. Fusion drives are permitted. Laser sails are permitted. And funded. And being engineered right now. Closed ecosystems are permitted. Spin gravity is permitted. Centuries-long machines are permitted. No referee has ever thrown a flag that says never. So what would the answer actually take? Run the list. An engine class beyond anything demonstrated. Operating flawlessly for centuries. An energy budget that treats decades of planetary output as loose change. A sealed biosphere that outruns our 16-month record by a factor of 300. On its first and only try. Reliability engineering that keeps a million-component city alive for 4 centuries without a shipyard. A solution to human biology in deep space that nobody has sketched. And an unbroken chain of teaching. Hundreds of links long. Through a town of people born into a voyage they never chose. Any one of those. Alone. Given enough centuries. I would bet on humanity solving. That has always been our best trick. But the ship does not need any one of them. The ship needs all of them. Finished. Funded. And working simultaneously. Integrated into a single machine. On its maiden voyage. With no test flight possible. Because the only full test of a 400-year mission is the mission. That is the sentence the whole night was building. So, let me say it clean. There is no single wall between humanity and the stars. And that is precisely the problem. One wall. Our species would tunnel through. We always have. What stands between us and the stars is a system of walls. Holding hands. Where every brick you remove from one gets mortared into another. The question was never whether the universe forbids us to leave. The universe forbids nothing. The question is whether a stack of merely possible things, each one at the edge of a civilization's reach, can all be made true at once, held true for centuries, and bet on, sight unseen, by the people writing the checks and the people boarding the ship. And there is one more page in the ledger. The quietest one, and I have been saving it, because it changes what every other page means. Even if every invoice gets paid, even if the city ship works, the biosphere holds. The chain of teaching never breaks, and the breaking burn lands the town of heirs in orbit around a new sun. There is a question tonight has never asked. What? Exactly. Arrived. Here is the question one more time. The one on the thumbnail. The one you clicked. Why will humanity never leave the solar system? You now know the answer is hiding inside the words themselves. Because leaving turns out to be 4 different achievements wearing one name, stacked like rungs on a ladder. And our species stands on a different rung than most people think. Rung 1 is escaping. And escaping is solved. It has been solved since the 1970s. 5 human machines are on solar escape trajectories right now. Pioneers 10 and 11. Voyagers 1 and 2. New horizons. And nothing in the universe can call them back. A tombstone can escape the solar system. Escape only requires speed. Purchased once. Rung 2 is traveling. Crossing to another star with a working machine. Inside useful time. And this rung is genuinely within sight. Starshot, or something shaped like it, can plausibly put a camera past Alpha Centauri within the lifetime of someone watching this video. Grams can travel. That sentence, which would have been fantasy a generation ago, is now an engineering schedule, and it is glorious. And notice what it carries. A camera. The rung holds grams. Rung 3 is arriving, stopping, staying. And this rung holds nothing human at all. Every escaping machine we have ever launched is a flyby forever. Every funded interstellar concept is a flyby forever. The braking problem doubles the ship that carries brakes. And no architecture on any drawing board carries a human payload through that doubling. Nothing our species has ever designed can stop at another star. And Rung 4 is surviving, arriving as a living community that steps off and continues. And Rung 4 is where the ladder disappears into fog, because Rung 4 requires the sealed town, the biosphere, the 4-century chain of teaching, the generations born aboard, every invoice from tonight paid in full at once. Our species' most ambitious rehearsal of the critical subsystem needed rescue oxygen after 16 months. On Earth, with the windows visible from the parking lot. So, watch the title resolve itself. A machine will leave the solar system. Machines already have. A camera may travel to another star while you are alive to see the pictures. But humanity leaving means Rung 4. Living people. Arriving. Staying. Continuing. And between Rung 2 and Rung 4 stands everything this night has priced. That distance is not one breakthrough wide. It is a civilization wide. And it must all hold at the same time. On the first try. Forever. I want to end where we started. Because the ending was always hiding in the beginning. Voyager 1 is still out there tonight. Right now. As you watch this. It is 25 billion kilometers away and gaining 61,000 more every hour. Running on a nuclear battery that loses 4 watts a year. Sometime in the coming years, perhaps in the 2030s, the power may finally fall too low. The last instrument will go dark, and the deep space network will point its great dishes at that patch of sky and hear nothing at all. For the first time in over 60 years, the team in Pasadena knows the day is coming. They speak about it the way you speak about a grandparent, and the spacecraft will not notice. It will keep going, silent and perfect, out through the space, the headlines called Interstellar, on toward the true border. Around the year 2300, it will enter the inner Oort cloud. Still less than 1/100th of the way to the edge. Some 30,000 years from now, about the time the paint from the Chauvet cave has aged another full human history, it will finally coast out of the sun's gravitational grip entirely. And the solar system will, at last, be behind it. It will carry the golden record. The sounds of surf and thunderstorms and heartbeats. Greetings in 55 languages. Chuck Berry. Bach. The brain waves of a woman in love. Etched in copper and plated in gold. Built to remain playable for 1 billion years. Long after the sun swells and takes the earth, that record will still exist. Drifting among the stars. Quite possibly the last physical proof that any of this, any of us, ever happened. So yes, something of humanity will leave the solar system. It masses 825 kilograms. It does not breathe. It cannot slow down. It cannot turn around. And it cannot come home. That is the one ticket out we have ever learned to buy. And tonight you know exactly why. And you know exactly what it would take to buy the other kind. The kind with a heartbeat aboard. And why every path to that ticket runs through a stack of merely possible miracles that must all come true at once and hold for centuries. Until they do. The most spacefaring species this planet has ever produced remains what it has always been. Home, bound to one star. In one neighborhood, on one half block of a map the size of America, dreaming accurately, for the first time in history, about exactly how far away the horizon really is. If tonight rearranged the way you see that horizon, a like and a subscribe genuinely help this channel keep building nights like this one. And there is a whole library of them waiting for you right here. The solar system is enormous. The exit is real, and the lights are still on at home. Good night.